Okay, this is a fairly tough problem because of the last part. It's called a non-trivial rate problem. And no, some of it's easy, but some of it's um, not. The first thing that's interesting is this is the first one you've probably ever seen where there are three reactants, not just two. And so we have to find the order of the reaction with respect to the bromide ion. And then this is called the bromate ion. And then this is the hydrogen ion. And this one actually is kind of tough, but I'll get there in a minute. So the first thing, if you remember, to find the order of the reaction with respect to bromide, you don't look at the bromide and you find a set of trials in which the second reactant doesn't change and the third reactant doesn't change. And on this one, I'm going to go to colors. Okay, so here's the thing. Between experiment 1 and 2, the bromide ion concentration doubles. The bromate ion concentration remains the same, and the hydrogen ion concentration remains the same. And if this changes, it can only be coming from the bromide because nothing else changed. And I'm going to erase this in a minute, but remember, I always do the later trial divided by the earlier trial. 5.00 times 10 to the negative 4 divided by 2.5 times 10 to the negative 4. Well, this would cancel this, and 2.5 goes into 5 exactly twice. So 2 to what power gives you 2? And so the first thing we know is that the respect of this reaction with respect to bromide is first. Why? Because when this doubled and this didn't change and this didn't change, this doubled. So when this doubled, the rate doubled. And so that's a one-to-one correlation or first order, however you want to think about it. Now, I'm going to erase all this stuff because it gets complicated. So now the next reactant, and you'll see with these non-trivial ones, is they're actually pretty nice to you. And I'm going to switch colors. I'm going to go red this time. Okay, so I want to find a set of trials to figure out what's going on with the bromate. I can use, I need to find a set of trials in which these two don't change. And so what happens is I could use 1 and 3 or 1 and 4 and 3 and 4 here. And I can use 1 and 2, 1 and 3, or 2 and 3 here. And so the overlap in is right here, because if I use 1 and 3, there's no change in the concentration of the first reactant, and there's no change. And now this is crazy because this actually, if you do, I'll come down here. Remember, always do the later trial divided by the earlier trial. If I do 0.00750 divided by 0.00500, I get 1.5. And then when I do 1 and 3 over here, and I do 3.75 times 10 to the negative 4 over 2.5 times 10 to the negative 4, this cancels this. 2.5 goes into 3.75, 1.75. So no change, no change. This went up 1.5. This went up 1.5. That's a one-to-one correlation. This is also 1. Now, here's where things get interesting. This is called a non-trivial rate problem for reasons that will become apparent in a moment. And, you know, it's not that bad. You guys, my students tend to be really good in algebra. So let's go, I don't know, let's go purple just for fun. Now, to find the order with respect to hydrogen, I have to find a set of trials in which, so I can use 1 when these two are held constant. But look at 1 and 3, 1 and 4, or 3 and 4. And here, if I use 1 and 3, no, that's changing. 3 and 4, that's changing. And 1 and 4, that's changing. And so the problem is there really isn't a set of trials in which both of these are held constant, and that's a non-trivial. So here's what I would suggest we're going to do. We're going to use 3 and 4. This is no change. This is 2. So this doubled, but we already know that this is to the first power. So we don't have to put a question mark there. We know it's 2 to the first power. This is 2. We don't know the order. That's what we're trying to figure out. And then when you do on a calculator 3.00 times 10 to the negative 3 divided by 3.75 times 10 to the negative 4, if you do that, it actually comes out to be 8. So this is what we know. 2, okay, this doesn't change, so we can ignore it. 2 to the first times 2 to the question mark equals 8. Well, let's get rid of this 2. So coming down here, so 2 to the question mark equals 4. And so when this doubled, this quadrupled, which means this order up here is actually 2. And that's a non-trivial rate problem. Let me again try to explain. When this wasn't changed and this was doubled and this was doubled, the rate went up by a factor of 8. And we know that a factor of 2 of this 8 is from this stuff. But 2 goes into 8 4 times. So the other thing that's causing the rate to come out has to be coming from the other thing that's changing. So that's kind of crazy. But if you look at it, it says, and then it says, okay, so there, the chart was just on the first page. So then I'm going to go to the next page. And the first question is, from the data given above, determine the order with each reactant. So we figured out that this was first order. And all that math I did was showed it. And this is first order, but this was second order. I remember on the AP exam, it's always going to be 0, 1, or 2. Then the next question is, write the rate law. Well, remember now, the rate is the rate law constant, which is little k, because big K is the equilibrium constant. We know that the bromide ion was first order. You don't have to write the 1, but I'm going to. The bromate ion was first order, but the hydrogen ion was second order. So that's the rate law. Next question, determine the value of the specific rate constant for the reaction at 298, include correct units. So basically, let me go back to blue. We just figured out on the previous page that the rate was equal to K times the concentration of the bromide ion times the concentration of the bromate ion times the concentration of the hydrogen ion squared. Well, if you want to solve for K, K is calculated by taking the rate at any trial, and I always use trial 1, divided by bromide times the concentration of bromate times the concentration of the hydrogen ion squared. And so I'm just going to keep scrolling down. In trial 1, the rate was, and units are important, 2.50 times 10 to the negative 4 molarity per second. And then because this is downstairs, I'm going to multiply by the reciprocal, 1 over 0.0100 molar times 1 over 0.00500 molar. And then because this is second order, I'm going to write it down twice because it's a little bit easier to keep track of units if you do that instead of squaring it, because sometimes you forget to square the unit. And so what happens is this cancels this, and so you end up with the number that comes out on the calculator is 5,000. I'm going to come back. Exactly 5,000. And then everything cancels upstairs, and then downstairs you have 1, 2, 3 molarities left, and then times seconds. And if you remember, we always said this would be a fourth order over, or sorry, it's hard for me to talk today. Fourth order overall, because 1 plus 1 plus 2 is 4. And remember, it's always 1 less than the overall order, so 1 less than 4 is 3. Now the problem is, switching colors, is this has 3 sig figs, and this has 3, and this has 3, and this has 3, and this has 3, but this has 1. And if I write it like this, it has 4. And if I write it like this, it has 5, and we need it to have 3. And so another thing that's tricky about this problem is we have to put it in scientific notation to get it to, okay, I'm going to have to hit extend page, sorry. We're going to have to put it into scientific notation to get 3. So 1, 2, 3. Best answer, 5.00 times 10 to the third, because 5 times 1,000 is 5,000. And then over molarity cubed times seconds, and that's the value of K. This is a very tricky problem, but very doable. All right, next question. Calculate the standard cell potential for the reaction using the information below. And this is kind of interesting, and I left room up here because remember, here's the overall reaction. It's from the first page, and when you take the AP exam, they'll have these, they'll have the 2 pages side by side, so you won't have to flip back and forth. So 5 Br minus plus I'm dropping the physical states, minus plus 6H plus goes to 3 Br2 plus 3H2O. And they want you to figure out the standard cell potential. Okay, so if you look at this, we need to have, because there's a 3 here and a 1 here, we need to take this reaction right here, and I think we need to triple it to get a 3 there. Did I get that right? Yep. And so what happens is I'm going to take this one and I'm going to flip it. So I'm going to go 2 Br minus goes to, sorry, I just said because of this 3 we're going to triple it. Well, I'll just do this. And then Br2 plus 2 electrons, and then E naught is negative 1.065. I'm just going to try to get these things where they belong. So now the bromine molecule is on the right, and the bromide ion is on the left. Now we need to get, the H needs to be on the right, and it is on the right, and so we have BrO3 minus plus 6H plus 5 electrons goes to 1/2 Br2 plus 3H2O, and E naught is 1.52 volts. Sorry, I forgot volts here. Okay, interesting phenomenon. Now, one thing we know about redox reactions is that, I'm going to switch colors, this and this have to be the same. By the way, this is on the right-hand side of the arrow, this on the left. So what's going to happen is the most important thing in redox is they have to be the same. I'm going to have to multiply this by 5 because that'll give me 10. And I'm going to have to multiply this whole thing by 2 because 2 times 5 will give me 10. And I'm going to do a better job of lining up the arrows. So right now we got 10 bromide goes to 5 bromine atoms plus 10 electrons. But remember, when you multiply, the cell voltage does not change because it is an intensive property. It does not depend on the amount of matter present. And so when you multiply, you don't multiply this, one of the few times. All right, so now I have 2 BrO3 plus 12 H plus 10 electrons goes to Br2 plus 6 H2O. And again, the cell voltage does not get multiplied because it does not depend on the amount of matter present. If I add these together, what would happen is, I'm going to hit extend page. So what would happen is I would have, okay, so this is, let me switch colors. This is on the left, this is on the right. And so I end up with 2Br minus, or 10Br minus, plus 2BrO3 minus, plus 12H2 goes to 6Br2 plus 6H2O. And then the cell voltage, this is interesting. When you add these together, you get positive 4.55 volts. But when you're adding, you count decimal places. This has 3, this has 2, you only get 2, so positive 0.46 volts. Now, one would say that this is twice as big as it should be. So if we divide everything by 2, we get 5Br minus plus 1BrO3 plus 6H2 goes to 3Br2 plus 3H2O. But remember, when you multiply or divide, you don't, it doesn't affect the cell voltage, because remember that this only occurs on the surface of the metal. It's where the liquid in the battery touches the electrode. So the mass of the electron has no parts. So this is the answer for D. It's 0.46 volts. And then here's the craziest part of all. Determine the number of electrons transferred in the overall reaction. And the answer is 5 electrons. I'm just going to say that. And I'm going to go back. Remember up here, when we did this, we canceled 10, we canceled 10. So for this reaction, there's 10 electrons. But we divide it in half. So half of 10 is 5. Hope that helped. I hope you understand that. Feel free to ask questions.